Okay, so last time we looked at how temperature increases the rate of reaction, and hopefully you remember that when you increase the temperature, the number of collisions increases. Each of those collisions is going to be more energetic, so the rate will increase. And obviously if they're more energetic, then more of those particles will have energy greater than the activation energy. And of course the idea was you could actually make predictions using that theory if you change, well, we just looked at temperature last time. So obviously as you increase the temperature, the rate of reaction increases. Then I very briefly talked about this idea of proportionality. I've got a question on that later in today's lesson. So today we're still going to be looking at rates of reaction, particularly though we're looking at concentration of solutions and also pressure in gases. It's essentially the same theory. Once again, you're going to hopefully be able to predict and explain the effect of changing concentration and pressure. And as I said, I've got a question later on which will look at this idea of proportionality. Right, first up, the commonest reaction that is looked at when you actually do this practically is this one between hydrochloric acid and calcium carbonate. First job, I'd like you to try and predict what you think the products will be. Make sure if you're writing your full equation out that it is a balanced full equation. And if you would like some clues, I will give them now. This is an acid and a metal carbonate. So from the unit C5, you should know that there are 3 products. Further clue, one of the products is something called a metal salt. One of them is from the carbonate part, and one of them tells you that this is a base. And to remind you, bases neutralize acids. So you should have come up with this. Hydrochloric acid plus calcium carbonate makes calcium chloride. That's the metal salt, obviously chloride because we had hydrochloric acid. Carbon dioxide, that came from the carbonates. And water, I told you that this was a base. A base neutralizes an acid, and if you neutralize an acid, you would always get water. Notice the state symbols. Hopefully you know what they all are. L, liquid, G for gas, AQ means aqueous or solution, and of course S is solid. So looking at the state symbols of those products, that's this side of course, how could you measure the rate? So obviously we've looked at ways of measuring rate in 8.1. What method would be a good one to use for this reaction? Right, so the methods that you can use are collection of gas. There are 2 ways of collecting gas. This one is the gas syringe that was in lesson 8.1. There is actually an alternative, which is a kind of simpler way of doing it, where you put a bung on a flask, put a delivery tube, gas comes down here, and basically you fill usually a measuring cylinder. They've got burette, but you usually use a measuring cylinder with water. Bubbles go up through it, and then of course you can measure how long it takes for that to empty and hence work out the rate. If you have a quick look at this YouTube clip, it's a good one which shows you the difference between these 2 methods, and then I will then talk you through one of them in particular. Okay, so the method we tend to use in lessons with this one is the gas syringe one. So here's your kind of standard gas syringe method. In actual fact, when we do it in class, we tend to use smaller time intervals and different concentration of acid to the next slide. However, I found a nice set of graphs that linked to the following concentrations. So this is a typical results table for this type of experiment. So you've got your time interval there of a minute, right? And then we are looking at 3 different concentrations of hydrochloric acid. So that would be your independent variable. Moles per decimeter cubed, of course, is the unit for concentration, and we're going to be looking at the volume of carbon dioxide collected in centimeters cubed. It's worth noting that gas syringes will hold up to 100 centimeters cubed. So this is a typical sort of graph you get for this type of experiment. You've got volume of gas on the y-axis, you've got time on the x-axis, and there are three lines. So there are three different concentrations. The capital M, by the way, stands for moles per decimeter cubed. And you can see the plots here. Now, a couple of things to mention here. Really, these lines should go back to the origin, because if you think about it, the only result that you are 100% certain of is that at time zero there is no gas, right? So it's standard procedure to put rates of reaction lines back to zero. Also, you will notice that there are no points beyond 50 centimeters cubed on this particular experiment. Now, I mentioned on the previous slide that our gas syringes hold up to 100. It would appear on this particular set of results, these ones only hold up to 50. So that would be why there's nothing else after that, and they have just extrapolated. That means basically continued on their best guess as to what's going on there. This type of graph, like I say, with different lines on it is very, very typical. So what if you wanted to actually calculate the rate of reaction? Now, you will notice in this particular case, I've asked you to calculate the initial rate of reaction. Now, this is useful because it enables you to compare quantitatively actually what happens when you change the concentration, as in using numbers. The reason being is because at the start, you know the concentration exactly. Now, you'll notice these are slightly different to the ones I had before, but we have a 0.5 mole per decimeter cube solution here, and then a 1 mole per decimeter cube solution, so double the concentration. Now, the only point in this entire experiment when that acid will be 0.5 moles per decimeter cubed will be right at the start. Reason being is because if it then starts reacting, the number of acid particles is actually going to go down over time, so the concentration will actually decrease over time. So the only time when you know that this is the actual concentration is at t equals 0, the initial point. So if you want to calculate the initial rate of reaction, just like before, you draw tangents. That's what this blue line and this red line are representing. So they are a tangent at t equals 0. So basically, you want it to just touch the curve at t equals 0 and then draw some straight lines. And you can see that we've got the two tangents drawn there. And just like before, you are going to do the gradient of those tangents to work out the rates. So for the first one, I'm sure you can work this out yourself. So give it a go. And you should come up with something like this. Make sure you include units, of course. 80, that's obviously the vertical y, divided by 30 gives 2.67 centimeters cubed per second. So that's 3 sig figs. Other one, 0.5, again, calculate that one. So you've got y over x. 80 divided by 60 gives 1.33 centimeters cubed second, again, 3 sig figs. So you will notice that there is a bit of a link, all right? If you look at what's happening here, when the concentration goes from 0.5 to 1, so the concentration doubles, what happens to the rate? Well, hopefully you can appreciate that the rate quite clearly has also doubled. Right, so this is just an alternative method for measuring the rate of reaction which produces a gas. You may well have come up with this when you were thinking about a way of measuring the reaction a few slides ago. Just a quick reminder, what you do is you put your acid and your marble chips or calcium carbonate, marble chips and calcium carbonate are the same thing, in your conical flask, and the carbon dioxide will come out, cotton wool bung stops the acid coming out, and then you measure the mass over time. And because the gas is coming out at the top, this mass will go down. That means you will get graphs for differing concentrations which will look something like this. So the blue one will be the lowest acid concentration because it is losing mass the slowest. This is obviously the steepest one here, so that is losing mass the quickest, so the carbon dioxide is being produced the quickest on the highest acid concentration. And again, they're all going flat because that point is where the reaction has finished. So why does this actually happen then? So we've looked at the graphs. We now need to look at the theory. So here's a couple of diagrams. And hopefully you can probably see, just from looking at them, why increasing the concentration of a chemical increases the rate. Now, there is an argument that actually, I know it says increased concentration there, probably should say increased pressure, because this looks very much like this is not a solution but a gas. However, as I said before at the beginning, the theory behind increasing concentration of a solution or increasing pressure of a gas is exactly the same. So basically, why is it that when you go over here and you increase either the concentration or the pressure, the reaction goes faster? Well, unsurprisingly, you can see there, in a higher concentration or a higher pressure, there are more particles in a given volume or in the same volume. It is important that you write this bit and don't just say more particles. It needs to be more particles in a given volume. Therefore, that means the number of collisions will increase, and more importantly, the number of successful collisions, i.e. ones that have energy greater than the activation energy. So to summarize, the rate of reaction increases as the concentration or pressure increases because, see if you can finish that up. There are more particles per unit volume, or more particles in a fixed volume. Make sure you are using the word volume, by the way, because it is three-dimensional. Therefore, there are more successful collisions. Right, finally, let's have a quick run through the specification statements just to check we're happy with them. So, first up, increasing the concentration of reactants in solution, pressure of reactant gases, and the surface area. Well, we didn't do that today, but that was last time. Increases the frequency of collisions, so increases rate. Hopefully you're okay with that. Hopefully you can predict and explain how changing concentration and pressure, temperature obviously was last time, affect the rate. And this idea about proportionality, this is when I was looking at that graph before. So when we doubled the concentration, the rate of reaction also doubled. Now the reason I'm saying this is if in an exam question, if they explicitly say the concentration is doubled or is multiplied by 4, you would be expected to say, therefore, the rate of reaction will double because there are twice as many particles, and therefore twice as many successful collisions.